Hello, Eastview Scholars. On this edition of Sharp Shorts, we're going to talk about trends in the periodic table. Based on this question I'm asking you here, with how this table is arranged, are there noticeable trends that help us understand properties of the different elements and how they interact? And we know that's true already. We have already looked at where metals are located, nonmetals are located, metalloids in between. We've talked about the properties they have. Now, recently, we looked at how ions are formed and how metals form positive ions, nonmetals form negative ions, and they like to interact in ionic bonds. So this is absolutely true. And here's a list of things we're going to look at, or things that are in your packet. Here we know, although you can't see them here, there's things we do know already about the periodic table and how it was organized, and your reading would help you understand that also in your work on your packet. But we know that we increase in atomic number for hydrogen 1 and helium 2 and lithium 3 and beryllium 4, and so we know we have an atomic number increase as we go. We also know that we are balancing that with, for example, all the S1 orbitals here and the S2s, and the noble gases have their S2p6 full electron shells, octet stable valence electrons. So we're balancing atomic number increasing, we're balancing having our outer valence electrons in the same row for the same families and everything else. And that leads to stuff, and here we can see, we know the nonmetals are in this corner and the metals are this way. And in that scale of how things change, more non-metallic characteristics this way, more non-metallic, more metallic that way. But there's other trends like atomic radius. Atoms get larger as they go down, but they also go from small to large, left to right. Ionization energy and electron affinity or electronegativity is more that we're going to look at. Are things that talk about how easy is it, how much do they want electrons, or how hard is it to take an electron away. And again, that just starts speaking to their ability to react and what properties they have. So we're not going to go through necessarily all of them. You have some in your packet that we picked out. But we do want to highlight some things that may help you understand the electron as we go through the year and the elements that we're working with. Here's the atomic radius. You can see by this diagram that the largest ones are in this corner, and the smallest one you can barely see here, fluorine, is right here. Okay, and you can see the trend is, if we ignore the noble gases, the trend is they get the atomic radius gets larger going to the left and down. Why is that? Well, down I can understand, because down means I'm adding more and more electrons in, so I'm just going to get bigger because I'm just taking up more space. Getting smaller as I go left to right, or larger as I go right to left, doesn't necessarily make so much sense, because if I am going this way across the period, across the row, I am adding in more electrons. So I'm adding in more electrons here and I'm getting larger, but I'm adding more electrons here and I'm going smaller. Well, remember, a row, everything is in the same energy level, filling in its S and P, or in this case d orbitals if I was in the 3d orbital and stuff like that. I'm adding more protons, I'm adding more electrons. So I'm creating a stronger nuclear charge, a more effective nuclear charge, and a tighter grip on those with more positive and negative, a tighter grip on the electrons that are there, which is why fluorine has the smallest atomic radius. It's the smallest size element out there, because it's got just that perfect amount that just really draws in those electrons and holds them tight. Whereas these are getting larger, they don't hold on to them tight because they're just getting farther and farther away, because you're going to higher energy levels all the time here. So the reason they do get smaller is you are staying in the same level and you are kind of sucking them in. Okay? But then that can give you an idea of these larger elements aren't going to really hold on. They're going to be very easy to get rid of their electrons and have their metallic and their higher metallic nature, say like conducting. Metals conduct well because they can so easily shed their electrons and stuff. Okay, and this is another one. This ionization energy and what we're going to talk about next, electronegativity, really go hand in hand. They're two sides of a coin. Ionization energy just says how much energy would it take to remove an electron. Well, down here in the metal end with very large atomic radii, it's not going to be that hard to remove an electron, because here's the nucleus, and that atom is farther and farther with francium, which you find over in europium. It's not going to be hard, it's not going to take much energy, because it's got a large number of electrons. These valence ones out here, boy, there's not a lot of attraction to the nucleus down here. There's not much energy holding onto it, plus the fact that it's being shielded by all the electrons before it. Where as I get to the nonmetals, and especially up in this corner where they're smaller, especially with a small atomic radius like fluorine, they're tightly bound. The energy it's going to take to remove an electron, especially since they don't want to get rid of electrons, is going to be incredibly higher. Okay? But again, that tells you how things react and how they behave as metals, nonmetals, and metalloids. Okay? Electronegativity, the other side of the coin there. Electronegativity talks about how badly do I want an electron. Fluorine, of course, being only needing one electron to fill out its shell and having a small atomic radius and stuff, will have a very high electronegativity. You want to grab it. In fact, it's given the highest number, roughly 4. In a value. Now magnesium on the other end of the table, even if it's not in the lower corner, but it's on the opposite side of the table in column 2, it wants to get rid of its electrons. It doesn't want more electrons. It wants to dump them to complete its shell. So its electronegativity number is very low. And what we look at, one of the things that makes this important is when we're trying to decide if something is an ionic or covalent bond, what you look at is in the difference in the electronegativity. And electronegativity, greater than about 1.7 tells you that it's going to have ionic bond properties. Where if it's lower than that, it's going to have covalent bond properties. So there is a lot of information that you can learn from just how the periodic table is set up. Reactivity, the last one we're really going to talk about and that you can work on in your packet. How vigorously will that substance react? Well, if you think of just the metal area, it's going to be that lower corner by francium. Reactivity decreases as you go left to right. So the closer you get to nonmetals, you get a little less reactive. Reactivity increases as you go down the group. So when you get down and close to that corner with francium, you're going to be very reactive because it's easy to get rid of those electrons. Whereas you get closer to the nonmetal, not that you're not going to be reactive, but you might not be as reactive. And then you think of some of the metals that are used closer to that metalloid, non-metalloid area, like copper and stuff for wiring, or in the old days, silver for wiring. They didn't, while they'll have reactions, they do last a lot longer because they don't react that well. Nonmetals now, the difference is now you've got that fluorine. In the nonmetals, it's about their higher electronegativity. They want those electrons, they want to form ions, and they want to be reactive. So fluorine is the most reactive of the nonmetals up in that far right corner because it has the greatest affinity to grab that electron. So anyhow, that kind of wraps up our look at the periodic table. We've gone through electron configurations and rows and groups and families and how to calculate atomic numbers and everything else. We've looked at how metals like to ionically bond with nonmetals. Nonmetals will covalently bond with each other and stuff like that. And we've looked at these trends, and you should be able to discuss those trends and how they lead to the properties that those things have. Anyhow, thanks for joining us on another edition of Sharp Shorts, and Scholar on, Eastview.